Lecture 11, Checkpointing and Rollback Recovery. Preface, recap of previous lecture. In previous lecture, we have discussed about different forms of consensus problem. Then it gives an overview of what forms the consensus are solvable under the different failure models and different assumptions on the synchrony and asynchrony. We have also covered the agreement in the category of synchronous message passing system with failures, asynchronous message passing system with failures. Content of this lecture. In this lecture, we will discuss about basic fundamentals and underlying principles of checkpointing and rollback recovery, and also discuss different rollback recovery schemes, that is checkpointing based rollback recovery and log based rollback recovery schemes. Introduction. The fault tolerance. An error is a manifestation of the fault that can lead to a failure in any system, that is shown over here. So a failure recovery is about either the backward recovery or a forward recovery. In forward recovery, the repair the erroneous part of the system state, and which is very difficult to predict and maintain at any point of time. So another way of failure recovery is the backward recovery. In backward recovery, you have to restore the system state to a previous error-free state, and it is done using operation-based method, and another is called state-based method, and state-based method is also called checkpointing / logging methods. So here in our discussion, we are basically looking up the backward recovery procedures for failure recovery. Rollback recovery algorithms, they restore the system back to a consistent state after a failure. Now they will achieve the fault tolerant by periodically saving the state of a process during the failure-free execution. They also treat the distributed application as a collection of a process that communicate over the network. So in the rollback recovery schemes, we will see how we have to restore the system using the states which we save at a particular instance of time, either through the checkpointing or through the logging method, or including both of them. So checkpoints. Checkpoint is a save state of a process. Now why is the rollback recovery of a distributed system is complicated? The messages here in distributed system induce inter-process dependencies during the failure-free operation. So this particular dependencies need to be maintained at the time of recovery, and that is why it is not so easy and it becomes complicated. Now another aspect here in rollback recovery is called rollback propagation. So the dependencies may force some of the processes that did not fail to roll back, and this is called rollback propagation. So it's not only the rollback of affected process, but all the processes which are dependent to that affected process has to roll back, and this will cascade this rollbacking of different process, and that is called rollback propagation. So this particular phenomenon of rollback propagation is called domino effect. Each process takes its checkpoint independently, then the system cannot avoid the domino effect, and this scheme is called independent or uncoordinated checkpointing. So the technique that avoids the domino effect are coordinated checkpointing rollback recovery. Here the processes coordinate with them to take their checkpoints such that the checkpoint form a system-wide consistent state globally. Now another type of or another technique is called communication-induced checkpointing rollback recovery. Here it forces each process to take checkpoints based on the information piggybacked on the application, and that is called the communication-induced. And so it has two different type of this one checkpointing. One is in the normal checkpointing, the other one is the forced checkpointing. Now another type of checkpointing is called rollback recovery, a log-based rollback recovery. It combines the checkpointing with logging of non-deterministic events, relies on the piecewise deterministic assumptions. Now preliminaries. These preliminaries are useful to see when we will discuss the details of checkpointing and rollback recovery. So in this preliminary, the first definition is about the local checkpoint. So all the processes save their local states at a certain instant of time. So a local checkpoint is nothing but a snapshot of a state of a process at a given instance. Assumptions. A process stores all local checkpoints on the stable storage. So a process is able to roll back to any of its existing local checkpoints. So the terminologies which are used here to represent the local checkpoint is represented by CIK. Here I is the ith process, and the kth local checkpoint which is taken at process I, and that is represented by CIK. CI0 is basically the process I takes the checkpoint CI0 before it starts the execution. Now consistent states. A global state of a distributed system is nothing but a collection of individual states of all participating processes and the states of a communication channel. Now this global state is a consistent global state, a global state that may occur during the failure-free execution of a distributed computing, and if a process states reflects a message receipts, then the state of the corresponding sender must reflect the sending of the message. That means in a consistent global state, if a message is received, then its send is also received. If that is maintained, then it is called consistent global state. So a global checkpoint is a set of local checkpoints, one from each process, and a consistent global checkpoint is having the similar definition as a consistent global state. That means a global checkpoint such that no message is sent by a process after taking its local checkpoint that is received by another process before taking its checkpoint. These are basically can be expressed and can be understood using these examples. So here we can see that this particular recovery line, which is shown as the dotted line, is forming a consistent checkpoints and is also a consistent state. So in this consistent state, you see that this message is send is recorded, but its received is not recorded, and there is no message whose receipt is recorded but send is not recorded. Hence it's a consistent state. Inconsistent state, here you can see that the receipt of a message is recorded in this particular checkpoint, but its send is not recorded in any of the collection of the checkpoint. Hence this collection of checkpoints is basically an inconsistent state. Now interaction with the outside world. A distributed system often interacts with the outside world to receive the input data or deliver the outcome of the computation. Outside world process OWP, a special process that interacts with the rest of the system through the message passing. A common approach: save each input message on the stable storage before allowing the application to process it, and parallel bars is a system that an interaction with the outside world to deliver the outcome of these particular messages. So there are different type of messages which we have to see under the preliminaries. So in transit message, a message that have been sent but not yet delivered, we will explain in the next figure. So the last message is the message whose send is done but the receive is undone due to the rollback, and that is called the lost message. Delayed messages, messages whose receive is not recorded but the receiving process was either down or the message arrived after the rollback, that we will see. Orphan messages, the messages with receive recorded but message sent not recorded, and these orphan messages do not arise if the process roll back to the consistent global state. Duplicate messages arises due to the message logging and replaying during the process recovery. Let us understand it in this particular diagram. Here the first case is about the messages which are in transit, so M1 and M2. So M1 is this particular message and M2 is this particular message. This is in transit, not yet delivered, and this is M2 also. Here M5 is also under transit. Last message is M1. Why M1 is last message? This message is lost. Why? Because there is a failure, and due to the failure, if it rollbacks to the previously consistent state or a previously consistent checkpoint state, then this particular receipt of this particular message will not be there. Message will, or the process will not be there to receive it. Hence, this is called a lost message. Due to the process not available to receive it, due to the failure or maybe some other reason. Now another type of message is called a delayed message. So let us say that if the message is in transit and this P1 recovers from this particular checkpoint number 8 onwards, and then basically it will receive the same message, then that particular message is called basically the delayed message. If the message is basically arrived late, then it is called the delayed message. So basically these are the example of a delayed message. Orphan, different assumptions on M4 and N5. This is M4 and N5, they are duplicated messages. Why? Because you see the dotted line is a recovery line. If the system rollbacks, so you can see that let us take the example of M4 first. So M4 is sent and its receipt is also basically recorded. Now when it has to roll back, then from the log this particular message, sending of M4 message, will be replayed again, resulting in another copy of the message M4 will be generated, and here on message or on process P4, that same copy will basically be sent again and will result into a duplicate messages here. Similarly here it is a failure, M5 is in transit, it will be received after some time, then again this particular message M5 send of a message is replayed again, so M5 will be duplicated. So these are basically the examples of different kind of messages here. So there are different issues in failure recovery. So the issues are like that there are three different processes, PI, PJ and PK. They will take their local checkpoints. For example, so P1, PI will take these local checkpoints. Similarly, the checkpoints which is taken by PJ is basically represented here. Similarly, the process PK will take its own local checkpoints, and there is a message from A to J which are flowing. Now here, when a system is failed, now it has to be restored in a consistent state. So consistent state would be to basically draw a recovery line or to find out a consistent global checkpoint state. So here after the failure it has to roll back from this particular checkpoint. So if this particular rollback is taking place, then the send of this particular H message will be undone in that case, and this, if it is undone, then this particular message H will result into a message which is called a orphan message. So because of the orphan message, the process Pj also has to roll back, and it will not be rolling back at Cj2, but it has to roll back at Cj1. So the recovery line is basically now following for Pi and Pj. Similarly, as far as Pk is concerned, Pk will not basically be able to roll back at Ck2. Why? Because of the same domino effect. Why? Because this message H will become an orphan message, and based on this particular message, so it has to roll back at this point. So this will form a recovery line, and this is shown over here in this particular example. So that consistent or restored global consistent state, and this is also called a recovery line. So the issue here is to find out among the set of checkpoints that particular consistent global checkpoint which basically will restore the system with a minimum loss is basically a quite challenging process, and that we are going to see through an algorithm how we are going to achieve it. So the rollback of a process I to a checkpoint Cij created an orphan that I have explained. Orphan message I is created due to the rollback of Pj that also have explained. Messages C, D, E, F are potentially problematic. Why? Because message C is a delayed message, message D is a lost message. So the lost message can be handled by having the processes to keep a message log of all the send messages. Message E and F, they are called delayed orphan messages. They are more difficult to handle. So after resuming execution from their checkpoints, the processes will generate both these particular messages. So these are basically going to be different issues in the failure recovery, and it requires coordinated or uncoordinated checkpointing. It also requires logging to replay the messages, and also basically how to recover. All these issues are quite intricate, quite complex, and need to be understood here in this particular concept. Now we are going to explain the domino effect. Domino effect is nothing but it's a rollback propagation or a cascaded rollback. So here domino effect, cascaded rollback, which causes the system to roll back to too far in the computation, even to the beginning, in spite of all the checkpoints. Here if you see that if the process P2 is failed at this point, then basically it has to roll back to the previous checkpoint, and this particular previous checkpoint will basically trigger on. Why? Because this particular message M6 will become orphan message. Once it's basically rolled back, will trigger the process P1 also to roll back. So the rollback of P2 will basically ensure that P1 also has to roll back. Now since P1 has rolled back, so this particular message will become orphan, and hence the P1 also has to roll back. So this will become a recovery line. P0 also has to roll back. So this particular rolling back of P2, which triggers the rollback of P1 as well as rollback of P0 from these checkpoints, is basically called a cascaded rollback, and this is called domino effect. Why? Because domino effect is, now you can see that it is due to the orphan messages. So orphan messages usually basically trigger the domino effect, and basically it is nothing but a cascaded rollback we have seen through this particular example. Now another problem is called the problem of a Livelock. So Livelock case here, where a single failure can cause infinite number of rollbacks. So Livelock problem may arise when the process roll back to its checkpoint after the failure and request all other affected process also to roll back. So in such a situation, if the rollback mechanism has no synchronization, it may lead to a Livelock problem as described in this particular example. So the difference between a domino effect and a Livelock here is that the domino effect is a cascaded rollback. As far as Livelock is concerned, it's an infinite rollbacks. So let us take an example of the Livelock problem. Now here in the case 1, if you see that process is failed at this point here, if it is failed, then it has to roll back to its previous checkpoint, which is shown as y1. If it's rolling back to a previous checkpoint, then it will basically result into an orphan message that is called M1, and this orphan message in turn will trigger process X also to roll back. So process X will roll back to its previous checkpoints. Now once process X roll backs, so this particular N1 will become orphan then in that case, and the previously sent message, if it is arrived here as a duplicate message, because if it is restart from here, so this particular sending of the message M1 will be replayed and that event will become N2. So basically here, so this particular message will arrive here, and this is an orphan message. Why? Because its send is undone and it is going to be received over here, and this will trigger the second rollback. So if this second rollback happens, then again this step number 1 will be repeated, and both step number 1 and 2 will be repeated infinitely, and this will lead to a Livelock problem, and this is all explained here. So the above sequence can repeat indefinitely, and this is called basically the Livelock. So in the recovery, how these algorithms are going to handle domino and the Livelock problems is going to be a difficult task. So that we will see in the further slides. Different rollback recovery schemes. Rollback recovery schemes can be classified into two different types. One is the checkpointing based rollback recovery scheme. The other is log based rollback recovery schemes. So checkpointing rollback recovery schemes are also classified into three different types. The first one is called uncoordinated checkpointing. The second one is called coordinated checkpointing. Third one is called communication-induced checkpointing. As far as coordinated checkpointing is concerned, that is also further classified into a blocking versus non-blocking checkpointing, and communication-induced checkpointing is also divided into two types, that is called model-based and index-based checkpointing. Log-based is also classified into three different types: pessimistic logging, optimistic logging, and causal logging. Checkpointing based recovery schemes. Overview. Checkpointing based recovery schemes are different type, as we have seen in the previous slides. Now we are going to touch upon each of them. The first one is called uncoordinated checkpointing. Here each process takes its checkpoints independently. Second, coordinated checkpointing. Process coordinate their checkpoints in order to save a system-wide consistent state. This consistent set of checkpoints can be used to bound the rollback. Third, communication-induced checkpointing. It forces each process to take checkpoints based on the information piggybacked on the application messages it receives from the other processes. Besides the normal checkpoints, whether it is coordinated or uncoordinated, it also includes the forced checkpoints, and this will basically further optimize the checkpoints in communication-induced checkpointing. So uncoordinated checkpointing, each process has autonomy in deciding when to take checkpoints. Advantage: the lower runtime overhead during the normal course of execution. Now it has many disadvantages. The first disadvantage is that this uncoordinated checkpointing may lead to a domino effect during the recovery. So that means dominoes are not avoided in uncoordinated checkpointing. Second disadvantage, recovery from the failure is slow. Why? Because the processes need to iterate to search a consistent set of checkpoints, and that is going to take a lot of time. Now each process maintains a multiple checkpoints and periodically invoke garbage collection algorithm, and this is another disadvantage of uncoordinated checkpointing process. Not suitable for the application with frequent output commits, and this is another disadvantage. So the processes record the dependencies among their checkpoints caused by the message exchange during failure-free operation, and tracking these dependencies are very important in restoring the system state after the failure. Now, how this particular dependency is to be tracked, that we can see here in this example or in this illustrative example. So direct dependency tracking technique: assume each process Pi starts its execution with an initial checkpoint Ci0, here Ci0 and Cj0. This is the initial checkpoint each process. Only there are two processes here in this example in the system, so they will take the initial checkpoints. Now then we are going to define a checkpoint interval. Checkpoint interval is represented by capital Ix, I comma x. That means, so I comma x is basically the interval between the checkpoints Ci x minus 1 to Ci x. This interval is represented by I, capital I comma x. So I comma x, that is checkpoint interval, is the interval between the two checkpoints of a process I between x minus 1th and xth. Now when a process Pj receives a message M during its interval, checkpoint interval, that is capital Ij comma y, it records the dependency from I, capital I comma x to capital I j comma y. So this particular dependency ensures that between these intervals the flow of message basically creates a dependency between these two processes, and once this dependency is saved onto a stable storage, and when the Pj takes its basically checkpoint Cjy. So these dependencies are basically tracked and they are stored, so that at the time of recovery in the uncoordinated checkpointing they will be used to basically eliminate or avoid the domino effect. Another type of checkpointing is called coordinated checkpointing. Coordinated checkpointing are of two types that we have seen in the previous slides. The first one is the blocking checkpointing. So after a process takes a local checkpoint to prevent the orphan messages, it remains blocked until the entire checkpointing activity is complete. So that means while the checkpointing is taking place, it is not allowed to send further messages, hence it is called a blocked state. The disadvantage here, the computation is blocked during the checkpointing state. Another type of checkpointing is called here non-blocking checkpointing. In the coordinated checkpointing, the processes need not stop their execution while taking the checkpoints. The fundamental problem here in coordinated checkpointing is to prevent a process from receiving application messages that could make the checkpoint inconsistent. So here the examples. checkpoint inconsistency, message M is sent by P0 after receiving a checkpoint request from a checkpoint coordinator. Assume M reaches P1 before checkpoint request. The situation results in an inconsistent checkpoint since the checkpoint. So this we can see in this particular illustrative example. So as we were talking about that this is the initiator of a checkpoint, so it will send this checkpoint request. So this particular request reaches at this instance to P0 and P0 will take its checkpoint, that is C0x, and after that it will send a message to P1. So P0 will send a message to M, and then the initiator process will come at this instant. So basically the clocks are not synchronized, or the communication channels are basically having sufficient delay, so that all the checkpoints are not basically carried out simultaneously, but in between these two checkpoints, these two processes checkpoint, just see that there is a flow of message. So what is to be done over here is that, so as soon as the checkpoint message is received and P0 is taking a checkpoint, it will send basically another message to the next particular process, that is its P1, and this P1 message will arise or will reach before the initiator's message could reach, and this particular P0 message will initiate P1 to take a checkpoint at this instance. So this particular message which P0 will send afterwards will receive after P1 has taken checkpoint, and this is the correct state. So the solution, as you know that it's a FIFO channels, so if the FIFO channels are there, then this problem can be avoided by preceding the first message post checkpoint message on each channel by a checkpoint request, forcing each process to take a checkpoint before receiving the first post checkpoint message, and that is being explained. Now third type of checkpointing is called communication-induced checkpointing. There are two types of checkpoints here in this category, the autonomous and forced checkpoint that I have basically explained to you before. So in a communication-induced checkpointing, piggybacks protocol related information on each application message. So this particular checkpointing information is piggybacked on the application messages. So the receiver of each application message is using this piggybacked information to determine it has to take a forced checkpoint to advance the global recovery line. The forced checkpoint must be taken before the application may process the content of the message. In contrast with the coordinated checkpointing, no special coordinated messages are exchanged. So autonomous checkpoints are the normal checkpoints, and forced checkpoints are sent through the message, which will basically, as mentioned over here, it will advance the global recovery line. So it will further optimize the recovery process. Two types of communication-induced checkpointing is there. One is called model-based checkpointing. The other one is called index-based checkpointing. In a model-based checkpointing, the system maintains the checkpoints and the communication structures that prevents the domino effect or achieve some even stronger properties. Index-based checkpointing, the system uses an indexing scheme for the local and forced checkpoints such that the checkpoints of the same index at all the process forms a consistent state. Log-based rollback recovery schemes. Log-based rollback recovery schemes, it combines checkpointing with logging of non-deterministic events. So it relies on piecewise deterministic assumptions, which postulates that all non-deterministic events that the process executes can be identified, and that the information necessary to replay each event during the recovery can be lost in the event's determinants. So by logging and replaying the non-deterministic events in their exact original order, the process can deterministically recreate its pre-failure state even if this state has not been checkpointed. So non-deterministic events are the the receipt of the event, the receipt of a message. So in this particular example, so the message which is received at this end, it cannot be determined, cannot be known when it is going to be received, but send of a message or a start of a process P0, that is basically called deterministic events. So important thing is for these deterministic, so these non-deterministic event, their deterministic parameters are to be basically found out and to be stored. So this is called the non-deterministic. And send of a message is a deterministic event. So log-based rollback recovery makes use of deterministic and non-deterministic events in the computation. Deterministic and non-deterministic events. As I explained you in the previous slide, the non-deterministic events can be the receipt of a message from another process, here like this, process I and process J. So this is the receipt of a message, is a non-deterministic. A message send event is not a non-deterministic event. So send is basically deterministic. The execution of a process P0, here when it starts, is a sequence of 4 intervals. Here it is shown. So it is the start of an event, and then so here the execution of P0 is the sequence of 4 deterministic events. So this is the deterministic event 1, this is the deterministic event 2, and this is deterministic event 3. 4 deterministic event. The first one starts with the creation of a process, while remaining 3 starts with the receipt of a message. This is 1, this is 2, this is 3, and this is 4. 3 starts with the receipt of a message M0, M3, M0, M3 and M7 respectively. So send event of the message M2 is uniquely determined by the initial state of the process P0 and by the receipt of a message M0, and therefore it is not a non-deterministic event. So that means with relation to the start of a process, you can understand or you can determine the instance when this send of this particular message is sent. Hence it is not a non-deterministic, it is a deterministic event. No orphan consistency condition, let E be a non-deterministic event that occurs at a process P. So depend E is basically the set of processes that are affected by a non-deterministic event E. This set consists of P and any process whose state depends on the event T according to the Lambert's happened before relation. Then log E, the set of processes that have logged a copy of E's determinants in their volatile memory. Stable, a predicate that is true if E's determinant is logged on the stable storage. Always no orphan condition. So that means if this condition is satisfied, then there is no possibility of any orphan message. So it says that if the dependencies are not stored in the stable, then basically it is stored in the log, or it is logged in the stable storage. Log-based recovery schemes differ in the way the determinants are logged onto the stable storage, and there are of 3 types: pessimistic logging, optimistic logging, and the causal logging. Pessimistic logging, the application has to block waiting for the determinants of each non-deterministic event to be stored on stable storage before the effects of that message can be seen by the other process or the outside world. Optimistic logging, the application does not block and the determinants are is pulled to the stable storage asynchronously. Casual logging, low failure, free overhead, and simpler recovery are combined by striking a balance between optimistic and a pessimistic logging. Pessimistic logging protocols assume that the failure can occur after any non-deterministic event in the computation. However, in reality, the failures are rare. Synchronous logging: if an event has not been logged on the stable storage, then no process can depend on it. Stronger than always, no orphan condition. So here, this is the example of a pessimistic logging. Suppose P1 and P2 fails here at this particular instance, then it will restart from checkpoints B and C. It will restart from B and C and roll forward using their determinants log to deliver again the same sequence of the messages as in the pre-failure execution. Once the recovery is complete, both the processes will be consistent with the state of P0, that includes the receipt of a message M7 from P1. So that means using the logging, it will be taken care of. Optimistic logging: processes log determinants asynchronously to the stable storage, optimistically assume that the logging will be complete before a failure occurs, do not implement always, no orphan condition. So to perform rollback correctly, optimistic logging protocol track casual dependencies during the failure-free execution. Optimistic logging protocols require non-trivial garbage collection schemes. Pessimistic protocols need only keep most recent checkpoints of each process, whereas optimistic may need to keep track of multiple checkpoints, and that will require more memory for storing the checkpoints. So in optimistic logging, consider the example. Suppose P2 fails before the determinant for M5 is logged. Here is logged onto the stable storage determinant, because determinants is this one, logged on a stable storage. Process P1 then becomes an orphan. Process P1 then becomes and must roll back to undo the effects of receiving the orphan message M6. The rollback of P1 further forces P0 to roll back to undo the effects of the receiving message M7. Why? Because this will become an orphan message. So it has to roll back. Why? Because its send is not recorded, because it has to roll back at this point. So this is called optimistic logging. Casual logging combines the advantage of both pessimistic and optimistic logging at the expense of more complex recovery protocol. So this particular example shows the casual logging. Checkpointing and recovery algorithms. Kutung coordinated checkpointing algorithm. Kutung in 1987 proposed a coordinated checkpointing and recovery technique that takes a consistent set of checkpointing and avoids domino effect and Livelock problems during the recovery. So we will see this is the algorithm which will basically use to solve the problem of domino effect and Livelock, and through the coordinated checkpointing. And it includes two parts. The first is called checkpointing algorithm, the other part is called recovery algorithm. In checkpointing algorithm, assumptions are that the algorithm assumes that the channels are following FIFO, that is, and it is also assuming that it is an end-to-end protocol and communication failures do not partition the network, and there is a single process for initiation and no process fails during the execution of the algorithm. So with this assumption, the checkpointing algorithms is basically as follows. So there are two kinds of checkpoints here in this algorithm. The first is called permanent, the another one is called tentative checkpoints. Permanent checkpoint is the local checkpoint, a part of a consistent global checkpoint. Tentative checkpoint, a temporary checkpoint, become permanent checkpoint when the algorithm terminates successfully. Now checkpointing algorithm it has two phases. In phase 1, the initiating process takes a tentative checkpoint and requests all other processes to take a tentative checkpoints. Now every process cannot send the message after taking the checkpoint. All processes will finally have the single same decision, do or discard. All processes will receive the final decision from the initiating process and act accordingly in the second phase. Now correctness, there are two reasons: either all of or none of the processes will decide and take the permanent checkpoint. So no process sends a message after taking a permanent checkpoint. Hence these two conditions basically ensures the correctness. Optimization may be that not all of the processes need to take the checkpoints. So if not change since the last checkpoints, so that particular checkpoint, that point no change since the last checkpoints. So there is a possibility of optimization here in the checkpointing phase. Now another part of this algorithm is called rollback recovery algorithm. Restore the system state to a consistent state after the failure with the assumptions. Have the single initiator, checkpoint and rollback recovery algorithms are not invoked concurrently. So rollback recovery has two phases. So the first phase says that initiating process send a message to all other process and ask for the preference, that is restarting to a previous checkpoints. All need to agree about either do or do not. So the initiating process then send the final decision to all the process and all the process acts accordingly after receiving the final decision for the rollback. So this algorithm we can explain what this algorithm is now doing. We can explain through this example. Here suppose process P want to establish a checkpoint at P3. This will record that Q1 was received from the process Q. To prevent Q1 from being orphaned, Q must also take the checkpoint as well. After sending the Q1, it has to take a checkpoint. Thus establishing a checkpoint at P3 forces Q to take a checkpoint to record that Q1 was sent. So this basically we can say that it is the Q2. This checkpoint, this P3 will force the process Q to take a checkpoint. So an algorithm for such coordinated checkpointing has two types of checkpoint: the tentative checkpoint and a permanent checkpoint that I have explained. So the process P first records its current state in the tentative checkpoint and then send a message to all other process from whom it has received a message since taking its last checkpoints. So call this set of such processes which are required to take a checkpoint, and basically it will be coordinated checkpointing as far as this particular process is concerned. So the message tells each process the last message that P has received from it before tentative checkpoint was taken. If that particular message was not recorded in a checkpoint by Q to prevent from being orphaned, Q was asked to take tentative checkpoints, and this is basically done here in this case. Now as far as rollback recovery, there is a possibility of optimization, and also there is a correctness that it will resume from a consistent state. Take this example: if there is a failure, it will roll back, or it will basically select X2 as the checkpoint, a consistent checkpoint. This will basically trigger that this particular message is orphan, and this will also lead Y to be taken into a checkpoints. So this recovery line is like this. Now here in this case, this particular algorithm, although has basically using its rollback able to find out the recovery line, but you can see here that Z from the previous checkpoint there is no event, no activity happened, so there is no need of basically rollback of the process Z, and that is the optimization. So may not to recover all the processes, since some of the processes did not change anything from the last checkpoint, and from the last checkpoint here the events are happening, so they have to roll back, but process Z does not have to roll back. So there is a possibility of optimization of this particular algorithm of the number of rollbacks processes who are required to be rolled back. Now few other algorithms for checkpointing and rollback recovery which are summarized over here. Zhuang and Venkatesan algorithm for asynchronous checkpointing. So we have seen the previous algorithm was synchronous checkpointing, this is an asynchronous checkpointing and recovery. And Manivanan and Singhal, they are quasi-synchronous checkpointing algorithm, and Peterson and Kern's algorithm is based on the vector time. And Hillary and Mostafi, they have given the communication-induced checkpointing algorithm. Conclusion: rollback recovery achieves the fault tolerance by periodically saving the state of a process during the failure-free execution and restarting from the saved state on the failure to reduce the amount of the lost computation. And this we have seen in several algorithms happening. So there are three basic approaches for checkpointing and failure recovery: uncoordinated, coordinated, and communication-induced checkpointing. And for log based we have seen pessimistic, optimistic, and causal logging. So over last 2 decades, checkpointing and failure recovery algorithm has been very active area of research, and several checkpointing and failure recovery algorithms have been proposed in designing the distributed applications. In this lecture we have described Kutung's coordinated checkpointing algorithm and given the overview of other algorithm. In upcoming lectures we will discuss the deadlock detection in the distributed system. Thank you.